to 3.2. Is the determinant of A transpose equal to the determinant of A? Yes, that's true. And the justification they gave for that was that if you do a cofactor expansion across the first row of A, that would be equivalent to doing a cofactor expansion across down the first column of A transpose. You'd get the exact same value for the determinant. All right, so the columns of A are linearly dependent if the determinant of A equals 0. True. If the determinant of A is 0, that means that A does not have an inverse, which means all the things in that list of the invertible matrix theorem are false. And one of the things in that list is linearly independent columns of A. So when the determinant is 0, the columns are linearly dependent. Determinant A of 0, A has no inverse, which means all of those things in the invertible matrix theorem are false. All right, if A and B are n by n matrices, then the determinant of A plus B is the determinant of A plus the determinant of B. False. That was a warning in the text. The determinant of A times B is the determinant of A times the determinant of B, but then they give you this warning, there is not an equivalent statement for addition. Performing a row operation on a matrix A always changes the determinant. False, because one of the row operations of the 3 produces no change to the determinant, right? The one where you multiply by a row and add to another row. No, you can get a max of 4 points. Maximum of 4 points today. You just had an extra opportunity to get one of your 4. Okay, so your take-home quiz is due today, but hold on to it till the end of class because you may have some time to discuss your answers with your classmates after the lesson. All right, so today we're going to learn a shorter method for computing determinants. So if you did your homework already, you'll be glad for this, right? Other than the cofactor expansion, as well as several computational properties of determinants. Yeah. Yes, thank you. Okay, so last class we learned how to find the determinant of a matrix using a cofactor expansion, going across a row or down a column. It's a time-consuming process. All the examples that I had you do in class and in your homework, they were sparse matrices, meaning there was a row or a column that had lots of zeros, so it didn't take that long. But if it didn't have lots of zeros, this could take a long time. So a faster way of finding the determinant of a matrix is to first use row reduction to put the matrix in echelon form. You don't have to go all the way to the identity matrix, but just put it in echelon form, which is a lower triangular, like this guy or this guy. Put it in echelon form, and then you can use the fact that the determinant of a triangular matrix is the product of the entries on the main diagonal. We discovered that last class. So the key to using this process is to know how row operations affect the determinant of a matrix. So this was like the main theorem of this section. I think it was called Theorem 3 or something. It says if you have a square matrix A and you use row reductions to turn it into matrix B, anytime you take a multiple of one row of A and add it to another row, the determinant doesn't change, right? You have this equal determinants. And then if you interchange 2 rows, the determinant of B is the opposite of the determinant of A, so you just have to take the negative. And if one row is multiplied by K to produce B, so you just multiply a row by a scalar, that's our third row operation, then that also scales the determinant. Yes. Yes, every time you switch rows, the determinant switches signs. You got it. If you do 2, it's back to the regular determinant. So these are 2 possibilities of square matrices in echelon form. They're both triangular, so the determinant is going to be the product of the entries on the main diagonal. In this guy, where you have a pivot in every column and a pivot in every row, we have a determinant that is non-zero because we have no zeros on the main diagonal. And in this guy, we are missing a pivot, which means we ended up with a 0 on the diagonal. Determinant is 0. So this guy has an inverse. This guy does not. Because this guy has n pivots, which means that was part of the invertible matrix theorem. N pivots means it has an inverse. This one is going to have fewer than n pivots, so it does not have an inverse. So you can, if it has a pivot in every column, because it's square, it will also have a pivot in every row. So as with a 2 by 2 matrix, any square matrix is invertible if its determinant is non-zero. So you can add the determinant non-zero to the invertible matrix theorem now. So now if you know A has an inverse, you know its determinant is non-zero, and everything else in that list is also true. If the determinant is 0, everything in that list is false. So one of the things in that list was that if the determinant is 0, that means that A is not invertible, it's singular, and so its columns would be linearly dependent, as would its rows. Because if the determinant of A is 0, so is the determinant of A transpose. Right, so this was one of your quiz questions. The determinant of A transpose is equal to the determinant of A. The determinant of A times B is equal to the determinant of A times the determinant of B. But in general, we don't have an equivalent formula for addition. And we'll see more properties come out in our demo and activities. All right, so I have a 4 by 4 matrix here. I want to compute its determinant. I know that it's asking me to compute a determinant because those are vertical lines and not square brackets. So that's just notation for determinant. So we want to compute the determinant of this thing. I could use a cofactor expansion like we did last class, but it would be pretty time consuming because I don't have a row or a column with a lot of zeros in it. So I would end up having to, I would probably choose column 1 because it's got 1 0. And then each of the entries in column 1 would be a factor. And then the second factor of the term would be the determinant of a 3 by 3 matrix, which is also time consuming to calculate. So instead, I'm going to use row operations to put this in echelon form. So what do you want to do first? I'm not going to use my calculator. It's a good thought, though. 3 row 1 to row 4. Okay, yeah, so that'll knock out that -3 in the bottom. So I have 1, 2, 0, 3. Yeah, we haven't done this in a while. So the determinant of this guy, of this matrix, is going to be the same. I'm not using equivalent because those lines represent the determinant of that matrix. Thank you. So the row operation I'm about to perform is to multiply one row by a number and add it to another row. That doesn't change the value of the determinant. So this is going to be equal to the determinant of this new row, this new matrix. It has a new row 4. Okay, so if I want to knock out that 3, I would take row 1, multiply by -3, and add it to row 4, so I get 0. -3 times -3 is 9, plus 10 is 19. 1 times -3 is, oh, +3. Yes, thank you, thank you. So it should be -9 plus 10 is 1. And then 1 times 3 is 3, plus -6 is -3. 2 times 3 is -6, plus 8 is 2. Okay, what should we get rid of next to try to put this in echelon form? The 2 in the first column, yeah. And to do that, I'm going to multiply row 1 by -2 and add it to row 2. So -2 times 1 is -2, so that's 0. Just put this in here. Okay, so -3 times -2 is 6, plus -5 is 1. 1 times -2 is -2, plus -1 is -3. -2 times -2 is -4, minus 2 is -6. Is this coming back to everybody? How we do? Because we haven't done this by hand in a long time. Okay, so determinant hasn't changed yet because I haven't done anything other than take a multiple of a row and add it to another row. Yeah, what did I? Yep. Yep. Thank you. Yeah, I was multiplying by -2. -2 times -2 is +4, minus 2 is +2. Right? Thank you. Yeah, yeah. If you have, so in order for, right, yeah. Yeah, as soon as you have either a row or a column of all zeros, or 2 rows or 2 columns that are the same, or 1 row that is a multiple of another row, or 1 column that's a multiple of another column, you would immediately be able to say these columns are not linearly independent, which means this matrix does not have an inverse, which means that the determinant of this thing has to be 0. So am I there? Where are they the same? Oh, row 2 and row 4 are the same. So I now know that those rows are not linearly independent, and I can just stop. But let's finish just for the sake of practicing the method. So at this point, I can see row 2 equals row 4, which means the rows are linearly dependent, which means that the determinant of my matrix equals 0. So dependent. The rows are linearly dependent. Yep. Because row 2 is equal to row 4, so you can write row 2 as a linear combination of the other rows. Take the weight of 0 on row 1 and row 3 and a weight of 1 on row 4. So linearly dependent means there is no inverse from the invertible matrix theorem, which means the determinant has to be 0. All right, so that's a great observation. Good. But just for the sake of practicing this, I'm going to keep going so that we put this into echelon form, multiply along the diagonals, and you'll see that the determinant does come out to be 0. Okay, so Iris, what were you suggesting? Yeah, okay, so I'm going to use row 2 to eliminate rows 3 and 4. Maybe I'll just do that in one step. So row 1 stays the same. Row 2 stays the same. And then I'm going to eliminate the -4 and the 1 in rows 3 and 4. So I'm going to use this 1. So first I'll multiply this whole row by 4 and add it to row 3. So I get 0, 0. -3 times 4 is -12, plus 5 is -7. And 2 times 4 is 8 plus 1 is 9. Did I do that right? Yeah. Yeah, okay. And then for eliminating the 1 here, I can just subtract. So I get 0, 0, yeah, 0, 0. And I now have a triangular matrix, right? I have zeros below my main diagonal. So here's my main diagonal. Zeros entirely below it. So this determinant is 1 times -7 times 0, which is 0. And like I said, we saw that coming, right? So based on the determinant, we know that these are linearly dependent. We already said that. All right, so I want to use the fact that when you multiply one row of the matrix A by a scalar, if your row operation is to just scale one row by k, then you also scale the determinant. Use that to find out what happens if you scale an entire matrix, every row of the matrix. Right, so let's just say I've got some matrix A, B, C, D, E, F, G, H, I, right? Oh yes, you're very close. Last class, we looked at this for a 2 by 2 matrix, and we came up with the formula k squared times the determinant of A. It's k to the n, because you have to multiply n rows by k, and every time you multiply a row by k, you have to scale the determinant by k. So, okay, so let's say the determinant of this thing will be some number, I don't know, d for determinant. So that this random matrix has some determinant d. If I scale this matrix, the entire matrix by k, I have to multiply every row by k. Every time you multiply a row by k, you have to scale the determinant. And this is going to have, in this particular case, it has 3 rows, but in the general case of an n by n, it would be k to the n times the determinant. You have to scale the determinant n times, once for each row that you multiply by. Yes. No. No, because we only actually look for determinants in square matrices. Yeah. So the determinant, we'll just write this out, of k times a scalar times a matrix, is k to the n times the determinant of a, assuming a is n by n. So you'll need that property later in the group activities.